lesson is about special lines in triangles, and it goes along with Module 1, Lessons 29 and 30 in Engage New York. In our last lesson, we proved that the midsegment of a triangle is parallel to the third side and half the length. In this video, we will prove that the medians of a triangle, meaning the lines connecting the vertex with the opposite midpoint, the medians of a triangle meet at a point. Let's get started. Next, we'll look at Lesson 30. And Lesson 30, we're talking about medians. And we haven't defined median yet, and so I'm not going to talk about this stuff. But I will tell you that the median is defined to be connecting this vertex with the opposite midpoint. And that is a median. Now, one thing about medians we're asked to prove is that all medians are concurrent, which means that all three medians intersect at the exact same point, and we'll prove that on the next page. This point of concurrency has a special name. It's called the centroid, or the center of gravity of a triangle. So if you were to have a plate that's the size of the triangle, you found the centroid, it would balance perfectly on that point because that is the center of gravity. The proof also shows that a length relationship for each median, the length from the vertex to the centroid, is twice the length from the centroid to the midpoint of the side. Let me show you that in a GeoGebra file. Here's a triangle, triangle ABC, and I have drawn in the three medians, meaning I've connected each vertex to the opposite midpoint. And this point of concurrency right here is the centroid. Now, the second property that we're going to prove is that this length from the centroid to the vertex is twice as long as the distance from the midpoint to the centroid. Again, this point right here is called the centroid. All right, let's work on the proof. So again, I've taken the image that's on page 166 and put it over here on the left so I can draw on the diagram as I go through this proof. I want you to draw on the diagram as well. On the right, I have the proof that's on page 166. In this proof, we are given triangle ABC with points D, E, and F as the midpoints of the sides. And we are asked to prove that the three medians of triangle ABC meet at a single point. That's part of our standards, is to prove that this is true. In number 1, we draw midsegments DE, which is drawn for you in the diagram, and we draw AE and DC and label their intersection as point G. First, we draw DE, which is one of the midsegments of the triangle. That's important. We'll use the properties we just proved in this proof. We will also draw segment AE and DC. Those are drawn for you already in the diagram. And we'll label their intersection right here as point G. 2, construct and label the midpoint of AG as point H. So this point right here is the midpoint of AG, and the midpoint of GC as point J. So this is the midpoint. Now I'll point out really quickly that HJ is the midsegment of this triangle down here. That's going to be important for us later on in this proof. Number 3, DE is parallel to AC. Well, that's true because DE is a midsegment of triangle ABC. Step 4, HJ is parallel to AC. Well, that's also true because it's a property of midsegments, and we're thinking about this triangle down here having midsegment HJ. In step 5, we're proving that DE is parallel to HJ. Well, DE is parallel to AC, and HJ is parallel to AC, so it makes sense that all three are parallel to each other. Now, the other property of midsegments is that it's twice the length. And because both of them are midsegments with AC, they are both half the length of AC. Which I'll point out means that DE is equal to HJ, because they both equal half of AC. Now I'm going to scroll up. Step 7 says that this quadrilateral DEJH is a parallelogram because it has two sides that are parallel and congruent. Now in step 8, we're using a property of parallelograms that we proved that the diagonals will bisect each other. And let me draw on the diagram. Step 9 says AH is equal to HG, and that's true because point H is the midpoint of segment AG. And CJ is equal to JG, again because J was constructed to be the midpoint of CG. Step 10 says that AH is equal to HG, which we just proved, which is also equal to GE, which we said earlier by substitution. Similarly, CJ is equal to JG, which is also equal to DG, which we proved earlier. All right, let me scroll up a bit more. Step 11 says AG is equal to 2 times GE, and CG is equal to 2 times GD by the segment addition property. That this is twice as long as this, and this is twice as long as this. Now 12 says we can complete steps 1 through 11, do the whole thing again to include the median from point B. The third median, BF, passes through point G, which divides into two segments such that the longer part is twice the shorter. So the same thing is true. We've just proved that this is going to be twice as long as this, that we've shown already for the other two medians in steps 1 through 11. 13 says the intersection point of the median divides each median into two parts with lengths in a ratio 2 to 1. Therefore, all the medians, because they're all in the ratio of 2 to 1, they will all be concurrent at that point. This lesson was about special lines and triangles, and we also talked about medians and the fact that the medians are concurrent at a point called the centroid. Thank you for watching.